back to the first APRG seminar of this new year 2025. And it is my pleasure to introduce today's speaker, Thian Bhui from Macquarie University. He shall be talking on Riesz transforms, Hardy spaces, and Campanato spaces associated with Laguerre expansions. So with this, I would like to invite him to deliver his talk, and I also request all the participants to mute their microphone. And okay, over to you.
Okay, and thank you very much for your invitation to give a talk in the harmonic analysis and BD seminar. And today, I will talk about the Riesz transforms and Hardy spaces and Campanato spaces associated with Laguerre expansions. And that's the plan of our talk today. Firstly, I would like to give some background on Laguerre operators and Laguerre functions. And also, then we move on to discuss on the main results and then the technical ingredients. And finally, we just sketch out like some main ideas in our group. And for the first part on the Laguerre operators, and we consider like the operators L nu, that's in the form. And in this case, the space of variables, that's act here, that's in 0 infinity to the power of n. And in this case, we consider like the higher dimensional case of the Laguerre operators. And we also consider like the derivative, and that's the derivative related to L nu. So that's a little bit different, with like the derivative we know that's the classical the derivative, and then we have like xj and minus 1 over xj and nu j plus 1 over 2. And for delta j here, that's like the new derivative, and we can find out like the adjoint of delta j, that's delta j star equal to this one. And the reason why, and we consider like the derivative delta j instead of like the normal derivative, because we have the relationship. That's like if we check the sigma j and delta j star and delta j, and then that's equal to L nu and minus 2 modulus of nu and plus n. And here modulus of nu here we shall mean like we check the sum of all components of nu. And for this reason, and we can think like delta j here, that's like the derivative with respect to L nu. And for the Laguerre functions, and we have the Laguerre functions defined like that. And in this case, we don't need to care too much about the formulas of the Laguerre functions. We need to focus on the following two important properties of the Laguerre functions. The first one is like the Laguerre functions are the eigen functions of L nu, and the corresponding eigenvectors equal to this one. And again, and I would like to emphasize that, recall that like in this case, the modulus of nu here means like nu 1 and plus nu 2 and plus on the way to nu n. And the system of all eigenfunctions or all Laguerre functions form an orthonormal basis for L2. So we just need to know the following two important properties. And therefore, we denote like L nu here, that's the self-adjoint extensions of L nu. And that's the very, very common properties, because when we know like the eigenvectors and the eigenvalues of the function L nu, and we can represent L nu f in that form. And we have the very important identity number one here. That's if we can consider the actions of the derivative on the eigen functions or on the Laguerre functions. And here, if we take like delta J, yeah, on phi k nu, and then we have this one. And the second one means like if we replace the derivative by the conjugate, and then we have this one. Okay, and for the first one, and you can see here, and nu here we increase by ej, and but for the lower index, and we have to minus ej. And in this case, E1, E2, and on the way to En, that's the standard basis, for Rn. Therefore, for example, E1 here, does it mean like the vectors in Rn, but the first term does E1, and on the other term does E0. All right, and now we consider the Riesz transform, because we have like the sigma of delta J star delta J equal to L nu. Therefore, we can define the Riesz transforms in that form. We check the delta J, and then acting on like the power, the fractional powers, of L nu. And for the study of the Riesz transforms in the context of orthogonal expansions were initiated by Mackenhook and Stein, and later on, and that's the becomes like the very active topics in harmonic analysis. And if we take care of like the LP boundedness of the Riesz transform here, and firstly on L2, and from L2, and because we have like the eigen functions and the eigen values, and we can represent the fractional powers of f in that form. And therefore, when we write in that form, and we consider the actions of delta J, so we have delta J acting on like the functions by nu k, and therefore we just use the identity number one here. Okay, the identity number one, and then we can obtain like the second identity, and from the second identities, and because the functions form the standard orthonormal basis for L2. Therefore, if we check the L2 norm of this one, and then we have the inequality, something like that. So it just means like the Riesz transform about it on L2. Okay, it's very similar to like the classical case when we consider like the Riesz transform of the Laplacians, and for the L2 boundedness of the Riesz transforms, and this is quite straightforward. And similarly, in these settings, and the L2 boundedness for the Riesz transforms is quite easy. And for the general case on LP, and I would like to provide an overview on these research directions. And firstly, for the Kn equal to 1, and the boundedness of the transforms was studied by Steinbach and Torias in 2003, Bentacore et al. In 2008 and 2013, and for nu is greater than -1. And at the endpoint, on the scale of BMO space, and for nu is greater than -1/2, and were investigated by Cha and Liu in 2012. And later on, I will explain why we need like nu here is greater than -1/2. Because when we consider like the Laguerre operators, and all the indices here, that's it, we require c greater than -1. But sometimes, and we have to restrict ourselves to consider the case like nu is greater than -1/2. And for the higher dimensional case, and I mean like when n is greater than or equal to 2, and
So,
the boundedness.
so nu greater than -12 means each coordinate is really greater than -12, right? What does the meaning of this statement? Nu is greater than -1. Means nu is equal to nu1, nu2, nu n.
Because in this case, that's n equal to 1.
No. What is the meaning of this statement? Nu greater than -1 means each coordinate is greater than -1.
No, because in this case n equal to 1, therefore we have only one new, not new 1, new 2, and new n.
Oh, okay. N is equal to 1.
Yeah,
Sorry.
yeah,
Sorry,
right.
sorry, sorry.
Okay,
N is equal to
that's all
okay.
right. Okay.
Okay.
And for the higher dimensional case, and when n is greater than or equal to 2, and we know only like the only one result that is due to Novak and Stembach, yeah, in 2007. And they consider like the Monty in the index, yeah, V1, V2, and Vn. And the condition they assume here that is Vi is greater than or equal to -1 on 2. But Vi doesn't belong to the interval -1/2 and 1/2. Roughly speaking, it just means like in this case, and Vi is greater than or equal to 1/2, or Vi is equal to -1/2. Okay, and then they prove that like the transforms is a canonical segment of operators. Means if we denote this one, that's the kernel of the transform, and we have like the size, the conditions, and the holder, the continuity condition, yeah, for the kernel of the transform. And I would like to emphasize that in this case, like the order of the smoothness that's equal to 1. Okay, and now we look at the picture here, yeah, to see and what the condition here means. For example, when n equal to 2, right, we have new 1 and new 2. And this condition, new I is greater than or equal to -1/2 and doesn't belong to this interval, just mean like in the bubble region. So this one, all right. And like the point here means like -1/2 and -1/2 and two rays, right? And from the point here and here, the first ray and the second ray is here. Okay, so it just means like for if we consider like all new i's that's greater than or equal to -1/2, and there's still like the reason here. Okay, and they didn't show that the Riesz transforms in the Canon segment operators that's still open. Okay, and now I would like to explain why we need, yeah, new e greater than -1 on 2. Yeah, because in the general, yeah, if we consider like the case that's in new in -1 to infinity to the power of n, and the Riesz transforms, yeah, might not be the Canon segment operators, and these conditions, yeah, guarantee that like the Riesz transform evaluated on LP for p from 1 to infinity. Yet if we assume that like at least, yeah, one index, yeah, less than -1 on 2, and the range, yeah, of p, yeah, could be like not from 1 to infinity. That is some smaller range, yeah, between 1 to infinity. And the second conditions, yeah, they assume like Vi doesn't belong to -1 on 2 and 1 on 2, yeah, because they need to perform some estimate on the radiance, yeah, of the kernel of the Riesz transform. And when they
Can you
perform
go back to your previous result a little bit?
this
You will
one,
be able
right?
to state it.
Okay, and these conditions, and this condition guarantee that like the Riesz transform evaluated on LP for on P between 1 to infinity. So that makes sense. If you didn't assume like Vi is greater than -1/2, for example, like Vi less than -1/2, and then the Riesz transform, yeah, is not the Canon segment operator. And for this condition, the second condition, yeah, because in the paper of Novak and Stembach, and they want to estimate like the radiance, yeah, of the kernel, and then they need this condition, and and in our point of views, and if within, yeah, this interval, and we cannot estimate like the radius of the kernel of the Riesz transform. Okay, and therefore it's natural to raise the questions on the open problem on the interval that's in -1 on 2 and to infinity to the power of n. All right, and therefore, and in the talk today, and we will focus on some results. The first one, that's we will study the boundiness of the Riesz transform for the full range, that's -1 on 2 to infinity to the power of n. And we also study like some function spaces related to L nu. And in this case, we focus on the maximal characterization for the Hardy space. And the second one, that's the duality of the Hardy space. And finally, and we will show that like the Riesz transform evaluated on the new function spaces. Okay, and for the first result, and on the Riesz transforms, and we would like to introduce the following notations. That is, nu min equal to the minimum of Vj. And J here, we just take care of like all the indices, so that like Vj is greater than, or sorry, strictly greater than -1 on 2. And with the convention, that's the infimum of the empty set equal to infinity. And we also set like gamma nu equal to the minimum of this one. Okay, it looks quite complicated, but we can illustrate by the following examples. For example, n equal to 1. N equal to 1, in this case, we have only one nu, right? And if nu equal to -1 on 2, nu equal to -1 on 2 mean like the set of indices here is empty, right? Because no nu is greater than -1 on 2. Therefore, in this case, we have v min, nu min equal to infinity. And if nu here is greater than -1 on 2, -1 on 2, therefore, in this case, according to the formula number 2 here, and we have nu min equal to nu. All right, and if nu equal to -1 on 2, because nu min equal to infinity. Therefore, according to the definitions of gamma nu, and we have to see the minimum of 1 and infinity plus 1 on 2, and then we have to see gamma nu equal to 1. And for the second case, if nu is greater than -1 on 2, and because nu min equal to nu, therefore we have gamma nu equal to the minimum of 1 and nu plus 1 on 2. So it just means like if nu is greater than 1 on 2, greater than or equal to 1 on 2, and then gamma nu equal to 1. Okay, and for the higher dimensional case, when n is greater than or equal to 2, and if we check nu I here, like similar to the conditions in the paper of Stembach and Novak, this one. And we can find out in this case gamma nu equal to 1. Because in this case you can see here for nu min here, and we have nu min here could be like equal to infinity. Infinity, if all the indices here are equal to -1 on 2. If this is not the case, and we can find like all v vj all nu j in the set of index I nu here, that's is greater than or equal to 1 on 2. Therefore, in this case, we have nu means is greater than or equal to 1 over 2. Therefore, according to the definition here, and we have gamma nu equal to 1. And in the general case, and if we have at least one j, so that nu j in this interval, and then in this case we have gamma nu belong to 0 and 1. Okay, and these observations is very useful to explain the theorem number 1 here. And for the theorem number 1 here, and we assume that nu here in -1 on 2 and to infinity to the power of n. And again, and we recall that like gamma nu equal to this one. Okay, and no restrictions on nu. According to the result of Steinbach here, and they need some conditions like this. And in the figure here, that's the purple region here. Okay, and including like the point here and then to right here, and here, and we relax all the conditions, and we just assume like nu here in -1 on 2 infinity to the power of n. And therefore in this case we can show that like the transforms is the Cannon-Zygmunt operators, and the main point is here. That's if we have like the gamma nu here, and the gamma nu here, if we consider like the similar conditions of like Steinbach and Novak, and we have in this case gamma nu equal to 1, gamma nu equal to 1, and then we recover like the result of Novak and Steinbach. And because in when if outside the reasons nu I is greater than or equal to -1 on 2, and nu I doesn't belong to the interval -half and half, and we can find at least one v nu I nu j in this interval, and in this case we have like gamma nu belong to 0 and 1. And so this is the reason why, and we have the index here that's less than 1. So this explain why, and in the paper of Novak and Steinbach, and then they have to assume like nu I is greater than or equal to -half, and nu I doesn't belong to this interval. Because when you have like at least one j, so that nu j in this interval, and gamma nu less than 1, therefore the estimate here not true. Okay, so we because in this case, and we need like some order less than 1. Okay, so that's the first result. And for some comments on the theorem number 1. For the case n equal to 1, and Novak and Steinbach also study for the case n equal to 1, and then they also obtain like the weighted estimate. But for the weighted estimate, and then they decompose like the Riesz kernels into two parts. That's in the local part and the global part. And for the local part, and that's like the Cannon-Zygmunt operators, and it's very easy to deal with like the local part. But for the global part, and then they have to yield like the weighted Hardy inequality for the weighted estimate. Therefore, in their results, and they couldn't obtain the Macquarie class for the weighted estimate for the Riesz transform. And in Bentacore, and in 2008 and 2013, and they also obtain like the boundedness of the Riesz transforms and the weighted estimate, but they can only obtain like the weighted estimate with like the power weight, not like the Macquarie weight. And because their methods relies heavily on the transparency methods, that's it, they compare like the Riesz transforms of the Laguerre operators and the Riesz transform of the Hermite operator H like this. Let's see 1/2 and minus Laplace and plus x squared on R. Okay, and we move on to the second part. That is about the Hardy spaces. And for the Hardy spaces, and we define the function pro nu here. That's 1/16, and the number 1/16 here is not essential. You can replace by 1/4, 1/8, or anything. It should be all right. And divide by the minimum of 1/x, and the norm of x, and 1 and xj, and j here in I nu. And I know here, let's see, we just check out all indices, so that new j is greater than -1 on 2. Okay, and some example, if we have all new j is strictly greater than -1 on 2, and then it's just simply the minimum of 1 over the norm of x and xj for all j. Okay, and if you check new j e equal to -1 on 2 for all j, and then the function rho here e equal to equivalent to 1/1 plus the norm of x. Okay, and for example, when n equal to 1, when n equal to 1, and if you check nu here equal to -1 on 2, and then it's just equivalent to 1/1 plus x. And if nu here is strictly greater than -1 on 2, and then in this case the function rho here is just the 1/16 of the minimum of 1 on x and x. And we have the lemma, if we check x and we check the rho of x, and we have the ball, and for any y in the ball here we multiply by 4, right? And in this case, when you check the values of the function rho at y and at x, and they are comparable. Okay, and now we can with the function rho here in number 3, and we can define the Hardy space like this. And the Hardy space here we have BQ, and we need rho nu atoms, right? And to emphasize that the atoms here depends on rho. And for the first and the second conditions, and quite similar to the classical one, right? For the classical atoms, and we need the support condition, and the size conditions, that's the LQ naught. And for the last conditions, if we don't care about the big ball, and that's exactly the same like the classical case, right? And we have the cancellation condition here, that's the integral of ax dx equal to 0, but we only require the cancellations if the radius of the ball here is less than the function rho at x0, that's in the center of the ball. So in some sense, and we can think of the Hardy space here the local Hardy space, but related to the function rho, because if you replace the pro here by 1, and you go back to the local Hardy space introduced by Goldberg, right? And in some sense, we can view the Hardy space here look like the local Hardy space. Okay, and this part is quite standard. That's for the atoms, and we can define the atomic Hardy space. And because for P here, we fix P here, and for Q, and for all Q's between in the set here, and then that's equivalent and that's quite standard, and I don't want to go into the further details. Okay, and now we introduce like another Hardy space defined by the maximal functions of the semi-loop. And if you remember, like for the classical Hardy space, and we can define the classical Hardy space by using like the maximal functions of the semi-loop of the Laplacians. I mean, if you replace L nu here by the Laplacians, and you go back to the maximal characterization for the Hardy space, and therefore, and we can define the Hardy space like this by using the maximal function of the semi-loop, and then our second result, as we can show that like if p between this range, and then like the Hardy space defined by the semi-loop, the maximal function here, and the Hardy space defined via the atoms related to the pro functions, and they are the same. Okay, and I would like to give some comments on the theorem number 2. For the case n equal to 1, n equal to 1 and p equal to 1, and nu is greater than minus 1 on 2. So in this case, the function pro x is defined by 1 over 16 of the minimum of x and 1 on x. And in this case, and the result was obtained in by Jabansky in 2008. Yeah, but the approach in of Jabansky is not applicable to the case b less than 1, and for the case n is greater than or equal to 2. And for the theory of the Hardy space related to the critical function rho nu, and we can see like the work of Yang and Zhou in 2011, and but in the paper of Yang and Zhou in 2011, they assume this condition, that's rho nu y and less than or equal to some constant and times this one. But actually, in this case, our function rho nu here doesn't satisfy the condition. For example, we consider the case like when n equal to 1, and we fix y between 0 and 1, and we let x tends to 0, because when n equal to 1 and rho nu x is defined by the minimum of the minimum of x and 1 on x. Therefore, in this case, the rho nu y equivalent to y. Okay, and rho nu x equivalent to x, and because x outside here, and the term x here, but the power here is less than 1. Therefore, when you let x tends to 0, and you can see like the right hand side tends to 0. Okay, meanwhile, we have the left hand side is equivalent to y. So this is the reason why, and our function doesn't satisfy this one. Therefore, like the methods in Yang and Zhou 2011, they cannot be applicable to our setting. And another point, and we can see in the later on, we can see like the hit kernel of L nu doesn't satisfy the following estimate, and the following estimate require for any n greater than 0. So for any n greater than 0, and we can find the constant c depends on n, so that the hit kernel of L nu satisfy this one. And actually, we do not have this condition, and we do not have like the Holder continuity. Means this one, the last one, for some epsilon between 0 and 1, and x minus x prime is less than square root of t. Okay, and as a counterpart of Hardy space, and we also have the Campanato spaces, and that's equal standard. And we yield the definition very similar to the classical case. Yeah, but for the small ball, right? For the big ball, when the radius is greater than this one, and we require a little bit different here. That's stronger than this one. That's we check 1 over the volume of B and 1 plus S over N, and the integral of B, of F over the ball B. And here XB, that's the same centers of B, and RB, that's like the radius of B. And we can show that in this case, and the duality of the Hardy space is equal to the Campanato space, defined by this one. All right, and now for the case n equal to 1 and p equal to 1 and nu is greater than minus 1 on 2, and in this case the function pro nu is defined by 1 over 16, the minimum of x, and 1 on x, and the result were obtained in by Chai and Liu in 2012, and their methods rely heavily on the structures of the half-life 0 infinity. Okay, and if we go back to the Riesz transforms, and we have like the Riesz transform evaluated on the new Hardy space, and on the new Campanato space. Yeah, but for the Hardy space, and we just restrict the range here to see from from n over n plus gamma nu and to 1. Okay, and for the case n equal to 1 and p equal to 1, nu is greater than minus 1 on 2, and we can find the similar result on the Bimo space, not the Campanato space. Mean like the Campanato space, but only with x equal to 0. Okay, and now we move on to like some technical ingredients for the main result. And firstly, and I'd like to present some results on the kernel estimate. And again, I just recall the definition of no min, right? And we use the notation that's a less than b to the power of minus infinity. We shall mean like for any n greater than 0, and we have a less than some constant depends on n times b to the power of minus n. Because we use this notation because we don't want to write the case when nu min equal to infinity. Okay, and for the robotation number 1, and this one, that's the hit kernel bt nu, that's the hit kernel of L nu, mean like the kernel of the semi-group e to the power minus t L nu, and delta here means like the derivative, and the derivative here, right? And delta, let's see, delta 1, delta 2, and all the way to delta n. And for xj, and we shall mean like delta j equal to this one. That's the usual derivative. But we have like the extra term xj and minus 1 over xj, and nu j plus 1 on 2. And we can show that in this case, and if we take like the new derivative on the hit kernels, and we also have like the Gaussian upper bound, and the first two terms, that's the Gaussian upper bound, Yeah, but like the last terms, and we have the extra terms, and because the last term here is less than 1, therefore the estimate here is better than the Gaussian upper bound. And because we have only here the minus nu mean, yeah, plus 1 on 2, because sometimes nu means it's just between 0 and 1. So this is the reason why, like I explained before, and we do not have this condition. This condition we require that like n, yeah, any number. Yeah, but actually, yeah, in this case, yeah, we have like exactly equal to nu mean, yeah, plus 1 on 2. And in some case, and the exponent here is strictly less than 1. Okay, and for if you consider like the mixed derivative, or in this case, let's see L equal to 0. If we take L equal to 0 and we do not have like the derivative here, right? And if you check like the usual derivative on the hit kernel, and we do not have the Gaussian upper bound, yeah, because we have the extra term here. I mean the red term here. Okay, therefore, when the red term here, yeah, because we have that's a rho mu nu j and yj here. Okay, when this one is very small and then the term it blow up, and in this case we cannot expect the Gaussian upper bound for for the term for the usual derivative of the hit kernel. And similarly, and if you here we check like the derivative, yeah, with respect to y, yeah, but here we check the derivative, yeah, with respect to xj. Okay, and the similar form, yeah, but we have like yj and xj here, yeah, that's the function pro, yeah, nu j, yeah, yj, and that's the function pro nu j and xj. All right, and we also, yeah, need the following, yeah, kernel estimate for, yeah, the operators. The first one, that's like the Riesz transform, right? And we combine with like the semi-loop. Okay, and we have, yeah, the kernel estimate like this. And here, and we have the point y estimate for this one. And if we take one more derivative, yeah, but with respect to y, and we have the extra term here, right? That's 1 over rho nu y. Okay, and now we begin with the proof of the theorem number 1, and the theorem number 1, and it just means like the Riesz transforms is a Cannon-Zygmunt operators. Okay, and we have the estimate, yeah, number 4, number 5, and number 6. And the first one, that's like, yeah, the size, yeah, estimate for the kernel of the Riesz transform. Okay, and we have the better estimate, right? Because we have the extra term here, because the extra term here, that's less than 1. And the second one, that's we just estimate like the radiance, yeah, of the kernel of the Riesz transform. And when we estimate the kernel of the Riesz transforms, and if we do not have the blue terms, and we can imply that, yeah, the Riesz transforms in the Cannon-Zygmunt operators, yeah, straight away. Yeah, but because we have the blue term here, and we need to perform some further, yeah, calculation. And the proof of the item 4, 5, 6 is quite straight away. For example, like we just write out the Riesz transforms, yeah, in terms of like, yeah, the kernel here in terms of like the hit kernel, right? And the hit kernel, and we let the action, yeah, of delta here, and for delta bt nu, and we just use the property here, let's see delta and bt nu, yeah, x and y. and we just substitute the estimate upper bound into here, and then we can find out the upper bound for the integrals here, that's equal to this one. And for the other estimate like number 5 and number 6, and we can perform in the same ways. Okay, and now for the proof of the theorem number 1 and from the estimate number 4, and we can imply that that's either the Riesz kernels is less than or equal to 1 over x minus y to the power of n. That's quite straightforward, right? Because the extra term here is less than 1. And for the second one, and if we check the Holder continuity conditions, and we consider two cases, like if x minus y prime greater than like the maximum of this one, and then we can write something like that. Okay, and instead of like checking the difference, and we can dominate the difference here by the sum of the absolute values. And for the sum of the absolute value here, and we just use the number 4 here, estimate number 4 here. Okay, and we write out something like that. And because in this case, x and x prime is greater than the maximum of this one and this one. Therefore, we can replace this one by y minus y prime, and we come up with this one. And the power nu means plus 1 on 2 here. That's it, like less than gamma nu, because gamma nu equal to the minimum of this 1 and 1. Therefore, it should be so right. And therefore, we need only to consider the case when y minus y prime is less than or equal to rho nu of y. And in this case, and we use the lemma number 1 to say that in this case, like rho nu y and rho nu y prime, that's equivalent. And therefore we use the estimate number 5, the estimate number 5 here, and the mean value theorems, and we can come up with this one. And this for the next slides, and we just expanded, multiply y minus y prime here, okay, and we expand into two terms, the blue term here, and like and the second term, and the second terms is very standard, and we need only to deal with like the term e1, and for the term e1 and the term e1 here, right? And because in this case, that's it, we have y minus y prime is less than rho nu y, and then we can raise this term to the power of nu gamma nu, because gamma nu is less than 1. And therefore we rewrite this one, but we ignore the first and the second term, right? We ignore the first and the second terms, and we just check like the last term here, and therefore it allows us to cancel out rho nu y and rho nu y. Therefore we come up with this one. Okay, so finally, and we have in this case like the Riesz transform kernels satisfies like the Holder continuity, and by using the same methods, and we can obtain the whole Holder continuity with respect to the first variable. And so this completes like the proof of the theorems number 1. And for the proof of the theorem number 2, and actually, and not normally, and we have to break into 2 steps. And the first step, that's it, we try to prove like this inclusion and this inclusion. Okay, but because we do not have enough time, and we just represent like the first step only. And the first step only, and that's equal standard, and we just check the atoms, and we check out like the maximal functions. M L nu here means like the supremum, of t greater than 0, of the semi-group, acting on A. Okay, and normally, and we back into two terms. And for the first terms, that's equal straightforward and quite standard. And we need only to check out like the second term here, right? And for the second terms, and we consider two cases. Like the first case, let's see r equal to rho nu x0, because in this case we do not have like the cancellation property. But this case is quite simple, and I don't want to. I would like to omit the detail here. For the case number two, and in this case, we have the cancellation property, and we just perform like the standard way, and we minus this one because in this case the integrals of ay equal to 0, and for that's the difference of two kernels, and therefore we use the mean value theorems and the Robogeson number two. Robogeson number two because in this case we want to estimate like the radiance of the hit kernels with respect to the second variable. So we need Robogeson number two. So this one, the first one here. Okay, and for the first one, and we have the red term here. Okay, for the first term, y minus y0 over square root of t, and it should be so right. Okay, and the trouble that's like the second term, and therefore by the standard argument, and we come up with like the term f1 and f2, and f1 is very simple and standard, and we don't want to check out, we don't want to give the details for f1, but for the term f2 here, and we just use this one. Because in this case r is less than these functions, therefore because gamma nu here is less than 1, therefore we have this property, right? And we replace this one. All right, and in this case, you see here, we try to eliminate pro nu x0, this term from this term and this term, and therefore from square root of t to the power of gamma nu, and we use the exponential term here, and therefore we can come up with like r over x minus x0 and to the power of gamma nu, and therefore later on, and we have like this one is less than this one, and we can check out like the LP norms of the term on the right hand side. So this is the reason why, and we come up with like the LP norm of the maximal functions less than or equal to 1. Okay, and for the proof of the theorem number 4, and for the number 4 here, we have two statements. The first statement say that like the root transform is bounded on the Hardy space, and the second one is bounded on the Campanato space. And I only give like some ideas on the proof of the first item. And we for the first items, and we can divide the proof into two steps. The step number 1, that's it, we try to prove like the Hardy space of related to the operators nu plus ej and path 2, and that is smaller than the Hardy space related to L nu, and that is just the direct consequence of the following property. Firstly, if we add 2 here, and then actually still the same, and the good reasoning for this one, that's it, because in this case L nu, and we have like the discrete spectrum, and we have the spectral gap between like the least eigenvalues and zero. So this is the reason why it doesn't matter if you plot two or any positive constants, and these two Hardy space still the same. And the second one, that's it, we based on like the atomic decompositions, the new atomic decompositions of the Hardy space, and like the relationship between two critical functions related to nu and nu plus ej. And I don't want to provide the details, but I would like to tell you that, and that's it, just the direct consequence from the following, the first one and the second one. Okay, and because like the Hardy space of this one is smaller than the Hardy space of this one, therefore we can prove like the stronger conclusion. That's it. We replace L nu by L nu plus EJ and plus two. It just means like that's it. The Hardy. We prove like the Riesz transform embodied from this Hardy space into the Hardy space, this Hardy space, right? Because this Hardy space is smaller than this Hardy space. Therefore, if we can prove like from HBL nu into HBL nu plus EJ, and then we can imply that the Riesz transform embodied on HBL nu. Okay, and that's quite standard. We split into two terms. And the first term is standard, right? And we need only to check out like the second term. And for the second terms, and we yield the property, and that's the very nice property for the Laguerre functions. That's it. Like we have delta j here, and if we check delta j out, and then we have to degree this one by ej. Therefore, I mean the second identity here. Okay, and that's the proof, of the second identity. And okay, I will go through quickly. Okay, and if we use these identities, and for we also consider two cases. The first case, and if RV equal to pro nu xb, and that's quite standard and no problem. And for the second case, and actually, we perform quite similar to the proof of the Hardy space here. Okay, and we also use the cancellation of the atoms, and we add this term, and we back into two term here. And for the first term, that's very standard. That's like the F1, and then we also perform some calculation on F2. And later on, and we can show that like the upper bound of this one is this one, and the LP norm of the term on the right hand side is less than or equal to some constants. So it means like the LP norm of the supremum of this one is less than or equal to 1. Therefore, we already show that like the Riesz transform embedded on the Hardy space. Okay, and here are the references. Okay, I would like to finish our talk here, and thank you so much for your attention.
Okay, thank you, Professor Bhui, for a nice talk. Are there any questions from audiences?
Yeah, I have questions.
Yep.
Yeah.
Yeah. Actually, can you go to your theorem 2?
Yeah, theorem 2. Yep.
Yeah. So in this theorem, so your exponent in P is up to some like n by n plus gamma nu. So means there's some lower bound. So means, is there any result? Means is there also true for up to 0? Means they're like a classical Hardy space.
Yeah, yeah. Thank you very much for the very nice questions. Yeah, actually, we can do for b close to 0. Yeah, but it still depends on nu. Okay, I would like to explain a little bit and for this case. Okay, and because the range of p here is from 1 and from n over n plus gamma nu and to 1, right? And gamma nu, and we define something like that. And if we want to study for the case like when the index b close to 0, and actually in this case gamma nu is equal to nu mean plus 1 on 2, and nu mean plus 1 on 2. Therefore, when the index nu close to, I mean, tend to infinities, and you have more p.
Okay.
Yeah, more p. And but in this case, and we have to prove the propositions for, I mean, the higher derivative. Not L equal to 0, 1, 2, but I mean for any L.
Right. So that also you have to, I think, you take some more moment condition or cancellation condition in the atoms.
Yeah, right. It look like if we remember, like when we want to prove like any singular integral about it on the Hardy space, I mean the classical Hardy space on HB, right? And if we want to prove like b equal to 0, and we need more cancellation property on the kernels, or we need, I mean, more derivative on the kernel, right?
Yeah, yes.
Yep. So this is the reason why if we want to study for p close to 0, and we need the higher derivative estimate on the hit kernel.
Right. Yeah. So for higher derivatives, means we have also this type of estimate is already known for higher derivative of the hit kernel.
For the higher derivative, and I think we can prove that.
Okay.
Yep.
I have another question about about this function rho. So actually, I'm curious to know that so this rho function is actually, if I remember, so they are similar type of function for Hermite operator, right? This type of function, and I think is behavior there. I saw. I mean, what I remember is this rho nu is some similarity same with the Hermite operator with this. I mean, if you compare with this Laguerre operator and Hermite operator, and if you compare this rho nu this function, there's some relation with them. So is there also a relation with the Hardy spaces or between to the correspond to Hermite operator and this Laguerre operator?
So sorry, can you repeat your questions, please?
Yeah. So my question basically is there any relation between the Hardy spaces correspond to Laguerre operator and Hermite operator?
Yeah, I see. Okay, and firstly, because these conditions, and actually, and the Hardy space related to the Laguerre operators is larger than the classical Hardy space, right?
Yeah.
Yep. Yeah, because we need only like the cancellation properties for only the small ball.
Right. Yes.
Right. And even like because pro here is defined by the minimum of this one, therefore pro nu here is less than or equal to 1/16, right? Yeah, 1/16. So even like if you compare with like the local Hardy space, it's still smaller than smaller than like the local Hardy space.
Yeah.
Yep.
So my question is basically about Hermite operator.
Sorry,
Means,
larger than local Hardy space. Sorry, larger than.
actually my question about Hermite operator means yeah, you are right for classical Euclidean, but I'm curious to know about Hermite operator and this Laguerre operator.
Hardy operators.
Not Hermite. Sorry.
Hermite. Okay, and Hermite, yeah, that's in the special case in this case. Okay, and if you check like this one is 0, right?
Yeah.
And you have the Hermite. Yeah, but the Hermite here, that's a like look like the Hermite, yeah, on the domain, yeah, not on the host base. Yeah, because in this case we did check ourselves, that's E0 infinity to the power of n. Yep. And if you want to compare with like the Hermite, and okay, and I can see you, it's very difficult to compare with the Hermite. Okay, and for example, when n equal to 1, right, and the Hermite means like this one. The Hermite corresponding to nu equal to -1 on 2, and the pro function exactly equal to like the minimum of 1 on x and 1 equivalent to 1 over 1 plus x.
Yeah.
All right, and when nu is greater than -1 on 2, and then the function rho here is equal to the minimum of 1 on x and x. So 1 on x and x here, that's e like, I think that's e less than the pro functions, yeah, in the Hermite case, right?
Okay.
Okay. So if less than, so in this case, it means like if less than, so so the hardest
That means
space in the
this
Laguerre case
Hardy space
is larger
for this.
than the Hermite case.
Yeah, I think yes.
Yep.
Yeah. Okay, thank you for your answer.
Yep.
So are there any, maybe I can ask one question. So is there any definite expression of this heat kernel in this means exact expression without estimate? Is there any exact expression?
Yeah, sure, for sure. And okay, and actually, yeah, in you can find the expressions, yeah, on the heat kernel, yeah, on the paper of Novak and Stembach in 2007.
And so the thing is, in the Euclidean case, if you really look at HT, so it's basically HT are constructed out of H1 by using dilation, right? So
Yep.
is this property there still in this case? So Euclidean case, this if you look at HT,
the
kernel
gradient,
HT,
right? The gradient, right? You sorry.
are you able to understand my question?
Okay. You mean the gradient of the heat kernel, right?
Yes. No. PT, sorry, not sorry. I am saying that in the Euclidean case, if you look at PT of X, say, right? Okay, so the thing is, you can get this PT out of P1 using some dilation structure of Rn. Okay.
Sorry.
Is it that? No, if you look at Euclidean case, heat kernel PT, okay.
Yep.
PT is obtained from P1 by this something like T to the power minus n by 2, P1 of X by T, right? Is this properties true for Euclidean this case?
You mean in the position number 1, right? Yep.
Okay, I will look back better. I will look back the paper of which you shared. Okay, so if there are there any questions from the audience? No. Okay, if there are no more questions, let us unmute and thank the speaker for a wonderful talk. Okay, so with this, I would like to really end the session. Okay.